So this is how we'd go about calculating the bond enthalpy for a reaction, or the enthalpy for a reaction using bond energies. So here we have our reactants and our products. So in order for this reaction to occur, I have to break these bonds and form these bonds. So in order to figure out the energy, you really have to draw the Lewis structure. So if I have CH4, this is what I have. And I have Cl2. And I'm just looking at the bonds. I'm not too worried about the lone pairs. And I'm making CH3 Cl plus HCl. So what I have to recognize is that I have four CH bonds. 4 CH bonds that have to be broken. I have one Cl bond that has to be broken. And I'm going to take that energy and subtract from it the energy that gets released when I form bonds. So I'm going to make 3 CH bonds, as indicated by these 3, plus 1 CCl bond, this one here, plus 1 HCl bond. And I'm going to use the bond energies in that table that you have in your packet. So the way this would work is, here's what I've written, is the change in bond energy for CH times 4 plus the change, this is energy in, and what I get out is the energy from forming these bonds. Okay, so I just plug in the values from the table. And when I do that, this is what I get, and I get a final value of negative 104 kilojoules, which means it's an exothermic reaction generating 104 kilojoules of energy. Okay, so try this one. Okay, welcome back. So I need to look at, I'm breaking one of those and one of these. That's going to be my positive energy. And what I get out is 2 HFs. That's energy released. So here's the equation for that. I plug in the numbers. And again, what I get is an exothermic reaction. Okay, the other thing I can look at besides bond enthalpy or bond strength is bond length, because the length of the bond is an indication of how strong it is. The shorter the bond, the stronger the bond. And what you'll notice here is that triple bonds are shorter and therefore stronger than double bonds. So if I look at just the 3 carbon bonds, the single bond is 1.54 angstroms, 1.34 angstroms for a double, and 1.2 angstroms for a triple. Okay, and you can see that throughout. And the smaller the atom, the smaller the bond. So because nitrogen is a smaller atom than carbon, the single bond for each, I'm going to have a smaller bond length for the nitrogen bond. So we can also measure an average bond length for different types. As the number of bonds between the atom increases as I go from single to double to triple, the bond length shortens. Another term that sometimes gets used is, if I have a single order, I can talk about its bond order. It's pretty simple here. Single bond has a bond order of 1, a double bond has a bond order of 2, and a triple bond has a bond order of 3. So try to answer this question. What is the bond order of the bonds in ozone? Okay, welcome back. As it turns out, the bond order is 1.5 because I have a bond order of 2 here and a bond order of 1 here. And remember, these are averages of the two, so I end up with a bond average of 1.5.